Log on, tune in, find out. Another good idea from Cambridge.
Okay, thank you. So today, to finish these three talks, I'll talk about, so let's see, so we did, until now, we set up the correspondence that gave us the identification of the character variety with the moduli space of G-Higgs bundles. So today I'll talk a little bit about some tools that we can use for studying this moduli space of G-Higgs bundles and thereby learn something about the character variety. So just put up the general picture again. So we have our character variety here on this side. Let's fix the topological invariant. On the other side, we have the moduli space of G-Higgs bundles on our Riemann surface. And essentially, this correspondence came about by looking at this intermediate gauge theory space of solutions. A phi to Hitchin's equations, so just schematically. Okay, so let's see. All right, so we looked at these pairs of an H connection and the Higgs field phi on this fixed H bundle over X. And we got these identifications. So we have the identification of the character variety with the moduli space of G-Higgs bundles. And so today, to study this, I'll talk a little bit about deformation theory of G-Higgs. Then I'll talk about the C star action. And on this, and how that helps us to study things like cohomology of this moduli space. And finally, I'll talk about some particular cases of G, which, from the point of view of the character varieties, are perhaps particularly interesting. So if G is the isometric group of a Hermitian symmetric space of non-compact type, some special things happen on this side, and then that tells us something about also the character variety. So I'll actually stick with my paradigmatic example of the symplectic group, or maybe I'll talk a little bit more about one or two other examples. Okay, so let's get started. So first, so let's just remind ourselves. So we take this G-Higgs bundle. So E over X with the principal HC bundle. This H. So we had our initial in general real group G and the maximal compact H. So we have this principal HC bundle, and we had our Higgs field living in here, where K is the canonical bundle, and remember we had the Gothen decomposition of the Lie algebra, the isotropy representation from HC to the general linear group of MC. So this was just restricting the adjoint representation to H. So we can also take the derivative of this. So that's just the derivative of the adjoint, so we just take some y here to the bracket. Okay, so the bracket is the derivative of conjugate of the adjoint. Okay. Okay, so all right, so let me introduce now the automorphism group of E phi. So that's just the group of automorphisms of E that preserve the Higgs field phi. So let me denote that by E phi. And then we can have an infinitesimal automorphism group so those are just endomorphisms of E, such that this that preserve the Higgs field again. So we get here so let's write that down as infinitesimal automorphisms of the principal bundle, which are just sections of the adjoint bundle, and then they should preserve infinitesimally the Higgs field, so it's such that C of bracket with phi is 0. Okay. So then we can introduce two kinds of simplicity of bundles. So simple if the automorphism group is, well, smallest possible. Okay, so what's smallest possible? So certainly the center of H acts trivially on the center of H always gives us automorphisms of the bundle, but it may not act trivially on this isotropy representation, so we should intersect with the kernel of this isotropy. And similarly, we can say that E phi is infinitesimally simple if the infinitesimal automorphism group is smallest possible, so just take the infinitesimal version of this. So the reason why we need both notions, they're not in general equivalent. Okay, so remark. Because if we were just thinking about vector bundles, this would be equivalent. And for Higgs, GLN, C Higgs bundles, these are equivalent notions. But in general, for G Higgs bundles, it's not the same. So here's an example. Let's see. So we can take this sp2r Higgs bundle obtained as follows. So let's take hang on, I want sp4r here. Okay, so remember that should be a rank. An sp4r Higgs bundle should be a rank 2 vector bundle. So let's take that as a direct sum of 2 line bundles, both square roots of the canonical but non-isomorphic. And then remember our Higgs field split into pieces, beta and gamma. So if out of this choice here we have a nice simple choice for beta and gamma, we can just write it. Remember. So we can take simply, let's say, beta to be just simply 0 and gamma to be this one. Okay. Remember, this should live in S2V tensor K, and this should live in S2V tensor dual tensor K. Okay, so this is defines as a nice sp4 Higgs bundle, and this is infinitesimally simple, but not simple. Okay, so let me now write down the deformation complex. So it's just a two-term complex of sheaves. Take EHC and use the bracket with the Higgs field to go to EMC. That's okay. So then that governs the okay, so that governs the deformation theory. So the infinitesimal, the space of all infinitesimal deformations of E phi is just the first hypercohomology of this. Similarly, the zeroth hypercohomology and this is actually just the infinitesimal automorphism space that I just defined. And the second, as you might expect, is the obstruction to smoothness. So should maybe qualify that a bit. I'll do that in a sec. So anyway, if this vanishes and if you don't have any kind of singularities coming from finite order automorphisms, then this is a smooth point of the moduli space. Okay, and you should here actually one should, in case our group is non-semi-simple, one should actually use a slight variation on this deformation complex. You should divide out by the center of GC. So let's say adapt slightly this complex if G is not semi-simple. You should essentially take the deformation complex for the adjoint group and check the vanishing of the H2 of that. So this, I guess, is kind of all very well-known stuff. There's a nice paper by Biswas and Ramanan where everything is worked out very carefully. So this is in the journal of the other mess. Okay, so all right, so that was just a few words about how to study infinitesimally these guys. So now let's try and get into find out or learn something about how to use the C-star action. Okay. So okay, let's say what the action is. It's clear that so C-star acts on the Higgs bundle moduli space. So if we take a complex number, we can simply multiply the Higgs field by that complex number. Okay, so that gives us a new G Higgs bundle. If we think of the moduli space in terms of, sometimes we might want to, in terms of solutions to Hitchin's equations, as up there in the middle, you should notice that then actually the equations are not generally preserved by the C star action. Okay, so if you want to act on the space of equations, you have to restrict to U1 in here. So it's just sometimes okay. All right. So let me, for the moment at least, think of the moduli space as the moduli space of solutions. Then you can use your reduction to each EH to actually define a nice scalar metric on the moduli space. So from this point of view, let's say moduli space. Has a scalar metric, and this action of the compact group is a Hamiltonian action. And you get a moment map. Which, so, write M D okay, to R. So take a solution to the equations, it's gauge equivalence class, to call this F to the L2 norm of phi. Okay, so this makes sense because we can take the pointwise norm of the Higgs field and integrate it up using, so I guess here we use, so actually it's also conformally invariant, this. You don't really need to choose a metric on the surface. Yeah?
How do you say you define the scalar metric?
Okay, well, so you, from that point of view, you think of, you should look at that. You should just look at the space of connections in Higgs fields, okay? So these are sections on some associated bundles, okay, to your initial bundle. So since you have the reduction, so essentially you have a metric on any associated bundle, okay? That's because it comes from the principal bundle with compact structure group. And then you can define an L2 metric on these infinite dimensional spaces, and then, okay. The solution space to the equation is a infinite dimensional subvariety of these infinite dimensional affine spaces, and then you have to check that the metric descends to the quotient. But since you're dividing by gauge transformation for the compact group, that functions. Okay. So in fact, if your group G were complex, that's the, yeah, you have. Let's see, that's a hyperkähler metric, as I alluded to before. Okay, so this is this moment map. Maybe say. So this is not quite the moment map. You have to multiply by some constant, which I always forget. So, anyways, it's up to a constant. All right. Okay, and let's just for now at least assume that our moduli space is smooth. Okay. Otherwise, I should probably have assumed that a bit before already, something to talk about that moment map condition. Okay, and then there's a very nice theorem which tells you, which is of course a very well-known theorem also, so which tells you that in this situation, that function tells you everything, or well, tells you a lot of things about the cohomology of the moduli space, more precisely. So this is a general theorem whenever you have this setup. that f, so this is an old theorem from the 50s, says that, it implies that f, this f, is a perfect Bott-Moss function. What does that mean? So that means that you have critical subvarieties. Okay, so it's not a Moss function. The isolated points are not necessarily, the critical points are not necessarily isolated, but you may have some critical subvarieties. Let me call them in lambda. Critical submanifolds, I should maybe say. And if you look at the normal bundle, then the Hessian of f restricted to the normal bundle is non-degenerate. So that's some sort of non-degeneracy condition again. So, so the Hessian of f is non-degenerate on the normal bundle. Nu in m lambda. Okay, so that's the condition for being a Bott-Moss function, and that being perfect, well, that was 1. And being perfect means that you can get the additive cohomology of your space out of the cohomologies of the critical subvarieties and the indices of this Moss function. So we define the index of this critical subvariety to be the dimension on the subbundle of the normal bundle on which the Hessian is negative definite. Okay, so then you get the Betti numbers as follows. So write down the generating function. That's the Poincare polynomial. Okay, that can be obtained by summing up over all critical submanifolds their Poincare polynomials, and then you have to modify by t to the index. Yeah, see, that's not readable. Okay. Right. So here's an important observation. So the moment map condition there tells you essentially that that the gradient of f up to multiplication by I is just the vector field generating the U1 action, the infinitesimal generator of the U1 action. So that means that the gradient vanishes exactly when that infinitesimal generator of the action vanishes. So your critical subvarieties, the ones where the gradient of f vanish, are just the fixed point sets. Okay, so moment map condition says that on f tells you that the union of the n lambdas is just equal to the fixed locus of this circle action. Okay, so So that helps you to, if you want to try to actually do something with this, you have to, of course, find these critical submanifolds. So that's nice because you can find these. You can find these fixed point loci. So I'll come back to that in a minute. But first, let me try to maybe, on the one hand, paint kind of a picture of the situation, and then also I'll relate this point of view of the U1 action and the moment map picture to a more algebraic picture using the C star action. So let me draw first the picture here. So this is a picture of the, well, let's say MD. I'm not putting Dolbeau there because I'm secretly thinking of it as a space of solutions to the equations, of course. So I have here my moment map. Since it's a norm, it's always positive. And notice that we have here an absolute minimum, which I might call N0, which is just the pairs E phi where phi vanish, obviously. So this is the locus phi equal to 0. That's the absolute minima. And then we have these higher critical subvarieties in lambda that somehow sit inside this moduli space. Okay. Then you also have some, so for each critical, right, you can look at two different, you can look at the unstable and stable manifolds for the gradient flow of the moment map. So you have some stuff that flows down here under the negative gradient flow. So let's call that U lambda plus, and the stuff that flows out, so the unstable manifold, oops, let's call that U lambda minus. Okay, so actually have this written as the union of all the U lambda pluses. Okay. You don't fill it up with the U lambda minuses because actually you don't have stuff that comes down from, well, you have stuff that doesn't come from any of the critical submanifolds. These are finite in number, obviously. Okay, so okay, so you can also get this picture in a different way. So different point of view, which by a theorem of Francis Kerwin is actually equivalent to this one, is to just look at the C star action and then if we take the, if we define, if we look at the E phi's such that, say, the limits when z goes to 0 of the equivalence class of E z phi belongs to n lambda, in fact, then that is just the same as that upwards Morse flow there, and similarly the one, you can take the limit as z goes to infinity and you get the U lambda minus. Okay, so this then gives you the Bialy-Nicki-Birol stratification of the moduli space that also Brent Doran was referring to. And then, of course, the Francis Kerwin's theorem says that the Morse stratification is the same as that. So. So these are really actually more or less equivalent points of view. So from this point of view of this algebraic stratification, it becomes clear that you can use it also to calculate, for instance, Hodge polynomials and things like that. And then you can get the Poincare polynomial as a special case. So. Okay. Yes, these are compact. Yes, yes. So that map, if there's proper. Okay, so if you want to carry out this, say this program to try to understand the moduli space from the understanding of the fixed loci, yeah, well, okay, then there are two things you have to do. You have to understand how to find the fixed loci. So let me just, for simplicity, and because that's all I'm going to need in a minute, anyway, let me just assume that we are in the case of GLNC. Okay, so you can do a general description, but for simplicity, let's just assume that. Then we're in the case of Higgs vector bundle, right? So E is a rank n vector bundle, and phi is this twisted endomorphism, and then it's easy to work out that E phi is fixed under the U1 action, or equivalently the C star action, if and only if it's of the form. So E decomposes as a direct sum of subbundles, say up to EP, and phi has weight 1 with respect to this decomposition. So phi sends EI to EI plus 1 tensor the canonical. Okay, so such a thing is called a complex variation of Hodge structure. Okay. So that's very nice. There are things that you can write down. You can try and study their moduli. That is in general not all that easy, but at least you have some sort of hold on them. Okay. Yes?
For a general group, can you somehow codify the information of the fixed loci, you said? Loci in terms of representations?
Right, I mean, so, well, what would it, yeah. Surely you can write down what it is. So let's see, I'm not sure I can give you an exact answer. But see, the thing is, what is this? This means you have a reduction to some subgroup of HC, right? And then you have to, so that would, so you have, this corresponds to some reductive subgroup of HC, okay? So there's some reduction there. And then you have to look at the isotropy representation, okay? That'll split up, and you'll have to say that phi has weight 1 with respect to that decomposition, okay? So, so in a sense, anyway, so I did just this example because maybe leave my information complex here, and then let's see what happens to that. So see, of course, you can think of that deformation complex in a sense if you think of it just a bundle that's almost like, it's not quite a Higgs bundle, but it's something reminiscent of it anyway. And if you look at EGC, well, maybe minus the adjoint action of phi, you see this there. So this is the adjoint Higgs bundle associated to your initial Higgs bundle, and your deformation complex in a sense is just See here we have the, if we had a complexified our Higgs bundle, we would be looking at this deformation complex, just because in the case when the group is complex, the isotropy is the same as HC. So in fact, our deformation complex is a subcomplex of this one here. So you could just apply then that if you have a fixed point in particular, then this here is also, this adjoint Higgs bundle is also going to be fixed, so it's going to split. And we get a corresponding splitting of this subcomplex here. So if E is fixed, then that one, this complex here, splits again as a direct sum of, say, CKs, where each CK is something of this kind. So let me call this ECK, so some well, the fact that the Higgs bundle has weight 1 means that it goes like this. Okay, so we have these subcomplexes of the deformation complex, the weight K subcomplex, and yes?
For the fixed low side, why can't you have like B sending EI to EI? Why does it go?
Why does it go? Well, okay. Well, so the way to see that is that if you have a fixed point, that means that E phi and E z phi are isomorphic. Okay, so you have some isomorphism. Say, okay, and then what you do is you so let's call this, I don't know what, G Z, okay. So what you do is you split E in generalized eigenspaces. For this is an automorphism of E, okay. So you split E in eigenspaces for this, or maybe generalized eigenspaces, and then you see what happens to phi, okay. And in the end, since you're multiplied by Z here, phi is not fixed, okay. Phi doesn't preserve the eigenspaces. Actually, it ends up having weight 1, right? Does that make sense? I mean, the point is that GZ fixes E, right? So if you take the eigenvalues, these eigenvalues can't commute with phi, because then certainly phi would not be sent to Z phi, right? That's why it has to move up by 1. Okay? All right, so in particular, we get our infinitesimal deformation space, which is just the tangent space to the moduli space. We get that split up as a direct sum of H1s of these complexes there. And then remember from over here, if we wanted to do this sort of Morse theoretic analysis, well, apart from knowing the n lambda, we also need to know the index. So then you check, you make a little calculation, and you see that the negative eigenspace for the Hessian corresponds exactly to the positive weight space. So the H1s with K positive. So that's just a calculation you make. And let me write it. So let me write index of n lambda. So remember, this was a real dimension, so I'm going to multiply by a 2. And that's just going to be twice the dimension then of h1 for k greater than 0. Okay, of course you can also get other information out of this. So for example, if you want to calculate the dimension of the critical submanifold itself, you just have to take the h1 of the 0 bit, and you can calculate the dimensions of all these strata, and of course it all adds up. Okay, let me just leave it like that. And then let's notice that, so the very basic question you might want to answer about your moduli space is whether it's connected or not. Okay, so from the point of the Morse theory, of course, what you have to check then is if that subspace of absolute minima, if that is connected. So that's particularly important. Oh, let's see, a particularly basic question. So for connectedness question, want equal to minima of f on the moduli space. So how can we detect that? Well, that's of course if the negative Norman bundle vanishes. So to find this, we have to find out when is this is characterized by the fact that the Morse index is 0. So so this is let's say that E phi, or maybe more correctly here, A phi.
This gives you all connection components for just your allowing other minima, or just the you're considering local minima, or just absolute?
Yes, thanks. I should say local minima, obviously, yes. I mean, it's true that it need not, and in general it is not. So, yeah, thanks for pointing that out. So, this picture is a good picture if indeed this is connected, right? But in general, you could, in theory, have another component of a minima, which may be down here, but it could be a bit further up, right? So you could have something like this. This is exactly the situation. We're analyzing it, whether this happens or not. So. Okay, so this represents a minimum of f, if and only if that is 0. So if and only if this h1 of k less than 0, e phi. So this is, of course, going to be already critical. Okay, so if that's equal to greater than 0, I think I should say. Yeah, greater than 0. If and only if that's equal to 0. And then there's a nice cohomological criterion for whether that vanishes. So see, if we look at this, certainly if this map here happens to be an isomorphism, the first hypercohomology has to vanish. Okay, but it turns out that that's actually also a sufficient condition. So this happens if and only if for all. So this is for all k greater than 0, and this happens if and only if that map is an isomorphism. So this holds for each k. Okay. Okay, so this here is a proposition, a theorem, if you want. Anyway, it's not totally trivial. You have to work a bit to show that. All right, so okay, let's look at what I need to say about the general picture. So let's look at some examples. Let me leave my picture and okay, I should perhaps say just a remark before moving on to the example. So there's a case in which this tells you, at least as far as connected components go, tells you everything you want to know, which is if G is actually a complex group. So if G is actually a complex group, connected, but then I'm assuming connected all the time, so I don't have to write that. So if G is complex, then in general you can use what I've just outlined to prove that for a fixed topological invariant, the Higgs moduli space is always connected.
Sometime long ago you assumed that this thing was smooth.
Yeah, actually I did assume that. So see, but if you so for the determination of the minima, you can get around these issues. Okay, so in general, if you want to calculate Betty numbers and so on, you're definitely in trouble if it's not smooth. If you're just worrying about connected components, okay, if you work, I mean, it's certainly an issue, but you can work around it. So but from what I said, certainly the path is only totally clear if it's smooth. Okay, so that was a remark. Now let's look at. Let me put that so can work around smoothness issues for pi naught. Well, I mean, each time you have to. In each case you're studying, you have to see if you can manage to do it right. So essentially, what you have to do is you identify to prove something like this, you identify the n naught, you prove by some means, whichever are appropriate for your situation, you prove that n naught is a connected subspace, and then just have to convince yourself that you have all local minima, and you're done, okay? So of course the problem is if you have some points higher up which are singular points of the moduli space, okay? So you have to by hand prove that such higher critical points cannot be minima. Okay. So that essentially means you have to construct by hand some deformations along which this function actually decreases. All right, so let's look at an example of the symplectic group. So, these the Higgs bundles were these triples V beta gamma, where beta was a section of S2V tensor K, and gamma is a section of S2V dual tensor K. And so our topological invariant in this case is just the degree of V. just as in the case of n equal 2, we have a Milnor-Wood inequality that you can prove using stability, so or semi-stability implies that degree of v in absolute value is less than n times g minus 1. And in fact, it implies more. So let me just write that already for later use. If n is equal to, if degree of v is equal to n times g minus 1, then in fact gamma thought of as a map from v to v dual tensor k must be an iso. Okay, so remember yesterday we were looking at gamma in the case n equal to 1. Gamma was a section of this bundle here. It had to be a non-zero section of this degree 0 bundle, so that was the trivial bundle. So that is a generalization of that fact that you can prove. Okay, so we have our moduli space nicely organized into subspaces according to the value of the topological class of V. So let's have these. Okay, so this is the locus where degree of V is equal to D. So we have all these spaces, and then let's okay, so let's see. So yeah, so moreover, let's see. So let's try and look at let's try to look at some subspace that could be a candidate for our space of minima. So what's the lowest piece we can get to inside this? So okay, so maybe I need to in fact, I should maybe have said a word more here. So the same argument here actually tells you that if degree of V is greater than 0, then gamma is a non-zero map. Okay, so this was exactly the argument we also saw yesterday in n equal to 2 case. It was very simple application of stability, and again, this is the case. So it turns out you can show, so you can't make gamma vanish in general, but you can make beta vanish. So we can look at some, let's call this n naught. Let me call it nd. Okay. So let's define that at least when d is bigger than 0 or bigger than or equal to 0. Let's define that to be the locus of v beta gamma such that beta vanishes. So you can prove that, so proposition, this is the absolute minimum of f on md. Okay, so if you can prove that that is the only minimum and that is connected, then you're done. Okay, you have proved that your md is connected. Okay, so all right, so it turns out that that's not so easy. And in fact, yeah. So let me say. So here's one question. is this connected? So, well, if we think of it, what is this space? It's the space of pairs, then just V gamma, right, since we killed the beta. So this is actually a space of kind of if we think of gamma as a k-valued quadratic form, this is kind of, this is not really a orthogonal bundle, but what you might call quadratic bundles, okay? So it's a bundle together with a quadratic form that takes values in some line bundle, okay? So it's an actual moduli space in itself to study in a sense. It's the sort of most simple case of nonlinear pairs. It turns out that this question is not so easy to answer. So certainly, well, it's easy enough if n is 1 or if n is 1. If n is 2, the answer is yes. So that's a theorem of Garcia-Prada and Mundet. For n greater than or equal to 3 in general, it's already an open question. So there's one case you can solve, which is the case of the maximal value of d. But yes, if d is equal to n times g minus 1. Okay. Why is that? Well, that's because of what I just wrote over there. See, when gamma is an isomorphism, this means that your quadratic form, k-valued quadratic form, is really everywhere non-degenerate. So if you twist down by a square root of the canonical, you get an honest orthogonal bundle. And you know that the moduli space of orthogonal bundle is connected. So that's why you can do that case. Using this, well, and then here's the but. So using this, you might think, okay, at least for the maximal value of this invariant here, you can count all components. And you can, but it turns out that this subspace of absolute minima is actually not the full subspace of minima. Okay, so and not that's what did I call it? So n d contains all minima only when d is less than n times g minus 1. Okay, so for this maximal case, you get more connected components. Okay, so let me write down maybe the theorem. So this is the number of connected components of mn times g minus 1 x is p2nr. So it's equal to 2 to the 2g. When n is equal to 1, it's equal to 3 times 2 to the 2g plus 2g minus 4 when n is equal to 2, and 3 to the 2g times 2 to the 2g when n is greater than or equal to 3. Okay, so this in this case is already classical. So this was in Hitchin's paper and already known by Goldman. This I did later, and then this I did with Garcia-Prada and Mundet. So, okay, so that indicates that that this maximal case of maximal invariant, maximal topological invariant is sort of particularly interesting. So I'm running out of time, so let me just elaborate, if I can have just 1 minute to elaborate a little bit on that remark I made before, the orthogonal bundle. So if we define, in this case, W to be equal to b tensor k to the minus a half, and q to be equal to then gamma, but twisted down by some suitable thing. And this is an orthogonal bundle. And we can take the other piece of the Higgs field, the beta piece, and so here we have gamma tensor 1, and beta also, if we twist that suitably, then you see that that becomes a map to W tensor k squared. So we can take this composition and call it psi, and then what are we obtaining? We're obtaining a pair WQ, some sort of Higgs field psi, but which is now k squared twisted. And also you should notice that actually it turns out to be symmetric just because beta was symmetric, so that means that this is a symmetric endomorphism of W with respect to that quadratic form. So let me write that as something like this. Tensored now by k squared. Okay, so if you remember one of the examples of d-Higgs bundles from yesterday was the case of SLNR. So this is essentially this is actually not an SLNR Higgs bundle, it's actually a GLNR Higgs bundle, okay, because the maximal compact here is the orthogonal, so the complexification gives us something like that. And the isotropy are the symmetric things with respect to the quadratic form, so this is exactly what C is. So we could call this some sort of twisted Higgs bundle because we have the wrong line bundle, so twisted GLNR Higgs bundle. Okay. So this turns out to be the first indication that there's quite an interesting general picture that you can study in general for isometry groups of Hermitian symmetric spaces of non-compact type, of which the symplectic group is the case. So I don't have time to go into that. So let me just say there are some generalizations to this case. So I'll be happy to talk to anybody who's interested in the tutorial, but I think I better stop here.